we present MoNeRF, a new method for ultra-fast radiance field reconstruction for monocularized data. MoNeRF takes an image sequence of inward-facing views where each monocular image shows a non-rigid deforming scene from a different angle and time frame. In as few as 7 minutes, our method reconstructs a radiance and deformation vector field to enable 360-degree spatial-temporal novel view synthesis. We also provide a new dataset with 12 human performances to demonstrate the applicability of our approach to real-world dynamic scenes. Besides fast training, MoNeRF achieves real-time frame rates that enable a user to freely explore the reconstructed scenes and deformations, both for synthetic and real-world data. Here you can see a user exploring a scene from the DNeRF dataset in our graphical user interface. Our method also works on real-world data, as shown by this example from our new dataset. Given a non-rigidly deforming scene, we record and segment the dynamic foreground from multiple camera views. For our real-world recordings, we monocularize the inputs by sampling a single camera view per time frame, which reduces the memory and computational requirements. Similar to the synthetic DNeRF dataset, our inputs then consist of a single monocular view per time frame. We train our model by iteratively shooting rays from a training camera and sample discrete points along those rays. The sample position and corresponding camera timestamp are then passed to a deformation component that estimates the three-dimensional deformation vector field. Our factorization-based deformation component disentangles temporal and spatial information by using individual MLP components. These networks estimate high-dimensional feature vectors for the position and timestamp, which are then linearly combined to obtain the final offset vector. The transformed positional sample is then fed to a canonical module representing the undeformed scene. First, we sample features from a multi-resolution hash grid. These are then processed by two shallow MLPs that regress the density and color at the discrete input position. We obtain the final ray color via estimation of the discrete integral over all samples. By comparing the estimated and ground truth pixel colors, we can iteratively update our model parameters to reconstruct the scene deformation and appearance. Similar to the recently introduced DNeRF, our approach takes a set of monocular images, each showing a unique time frame from varying inward-facing viewing angles. To recreate the setup for real-world data, we capture 10 full-body human performances using a large multi-view camera setup and monocularize the recordings. Our final scenes feature human motion in various challenging scenarios, including self-occlusion, large complex motion, swinging loose garment, interaction with non-rigidly deforming objects, and complicated texture patterns. We additionally capture two challenging facial performances using a smaller upper body multi-view setup. These sequences feature complex, non-rigid deformations with topological changes. We compare our MoNerve against the recent NR-nerve and D-nerve approaches by rendering a static novel view for various sequences from the synthetic D-nerve dataset. Compared to other approaches, our method produces detailed results with high frequencies in a substantially shorter training time. Also, the reconstructed motion is more stable and temporally consistent due to the explicit scene representation and smooth temporal input encoding. We further evaluate MoNerve on the test set of our new real-world dataset. Again, our technique retains finer motion details in swinging garments and better preserves the texture patterns. Even for the challenging facial performances captured by fewer cameras, our method produces sharper results. While inconsistencies in camera calibration and foreground segmentation can cause artifacts in the eye region, MoNerve recovers more detailed and temporally consistent non-rigid deformations. We also test our approach on a continuous camera trajectory provided by NR-nerve. For comparison, we render the temporal deformations from one static input view. Again, our method achieves sharper and more detailed renderings, but also produces artifacts in the region of the arm, as it was not observed in all input views. In the future, dedicated regularizers can be investigated to adapt our method for such scenarios. Thank you for watching.